Very well. Great. So let me introduce our speaker for today. So she did her master's in Lund in Sweden. She just told us that she's from there. After that, she did her PhD in the University of Amsterdam in the Netherlands. In 2019, she finished, from what I understand, and she moved as a postdoc to Carnegie Observatories in Pasadena, where she first started as an Alvin E. Nashman Fellow in Theoretical Astrophysics, and since 2020 in a Hubble there. So without further ado, please, Silva, you, you can start now. Thank you very much for accepting our invitation.
Thank you very much. Let's see if I can find again the slides. Like this. You can see it? Okay, excellent.
Yes.
Super. So thank you so much for inviting me. I'm really excited to visit UNAM, even though this is virtual. Yeah, as you had much of visiting last week, probably you had a little bit of introduction to binaries, but I will anyway take some time to go through the basics in the beginning. So my name is Ylva Göthberg, and I work with interacting binaries. And today I'm going to talk mostly about stars that are stripped of their hydrogen-rich envelope through mass transfer, something you can see in the background of this slide, and how that can give rise to a large amount of ionizing emission and even provide sources of gravitational waves. In the end, I'm going to also show you some of the new work that I'm working on at the moment that is branching over to observation. So in the base, so to say, I am working on theory and computations. So binary stars are really, really quite common. So here we can see a diagram from Matt Moe and Rosanne Di Stefano in 2017, where the fraction of stars that are in a binary is shown on the y-axis, and the mass of the most massive star in the system is shown on the x-axis. So for a star like the Sun, about 15% of the stars are in a binary. So this binary fraction is the fraction of stars that are in such tight binary that interaction is likely to occur. So in fact, about 50% of solar type stars are in binaries, but about 15 will interact with their companions. Still a very large fraction, right? Given that there is so many solar type stars. But this increases with mass, and for the most massive stars above 10 solar masses or so, interaction is what happens most often to stars. You can even see that for these like 20 solar mass stars, it's over 1. So what does that mean? We tend to think of for this plot. This was because the O-type stars are in so tight binaries and multiple systems, so they actually have so many companions nearby that they can interact with. So this is really complicated. But today we're going to stick to just the binaries and what can happen then. This diagram is a chart from NASA where they show stellar evolution. Basically, this is the idea. So for a low mass star, how it's becoming like a giant star, and then eventually a white dwarf. But a more massive star, it maybe swells up to a red supergiant and then explodes in a supernova, become a neutron star or black hole. You can see that this is really quite simplistic. Given what we just were looking at, I would say it's wrong for the high mass end, right? Because most of these stars are in so tight binaries that they will not evolve like this. They will evolve differently. So how will they evolve then? This, I think, is a really nice GIF to show. It's actual data. It's from Beta Lyrae. Beta Lyrae is a nearby binary star, 300 parsec away, and it's on a 13-day orbit. The more evolved star in this system is 3 solar masses. It's the dark one in the image, And the less evolved star is 13 solar masses. It's the fainter object here. So by the fact that the more evolved star is lower, has a lower mass, it simply means that interaction is occurring. You can also see that from the deformation of the 3 solar mass star, the dark star here. It is drop shaped, it's transferring material to its companions. This is ongoing mass transfer.
Sorry, quick question.
Yes.
What is a Chara array? Where is it?
Ah, nice question. Yeah, the Chara array is located actually up the mountain here. It is an interferometer, and they can resolve things that are nearby. So the Chara array have, for example, resolved stellar disks, and it's one of the few instruments that you can actually like see how large is a star, right? Because in most cases the stars are unresolved when you look at them. So Chara array, yeah, it has some really cool stuff. One of them is this resolved binary.
Okay, thank you.
Then there is other ways that binaries can also interact. There is this example from Leonardo Almeida in 2015, where he found a binary that has a really, really smooth light curve and 2 components that seem to have similar radial velocity shifts, and the orbit seems to be really circular. So from these, they could understand that, you know, this is an massive over contact binary. It's sharing about 30% of the mass in this part of the peanut in the middle there. And what's happening to this star, I would say, is it's still a little bit unclear. There is studies for whether this is undergoing really extreme rotational mixing because of the very, very tight orbit, or alternatively that it's going to lead to a merger. And I think that these are really quite interesting systems. There is a search ongoing for more of these, but so far we know this one. So how common are these? This pie chart is created from galactic clusters of massive stars. And it's from a study of Sana and collaborators in 2012, when they found that 70% of all massive stars should interact in binaries. How do they interact? About 30% they lose their hydrogen-rich envelope through mass transfer. About 15% are the accretors of that system. So why is this not the same? It's because often the second star, the accretor, is a little bit lower mass and was therefore not included in the study of the most massive stars. And maybe a quarter will lead to this kind of merger and peanuts. So this can lead to a large variety of really interesting different things. For example, weird supernovae, stripped envelope supernovae, hydrogen poor supernovae, X-ray emission, right, from the accretion onto compact objects, or even like the creation of Thorne-Rydkop objects is theoretized, right? You can merge and have a neutron star in the center of a red supergiant. So I'm going to focus on the largest part in this pie chart, the envelope stripping, and what the resulting stripped star is capable of doing. So let's make a little outline here for the rest of the talk. First, what are really these stripped stars? And then how do their ionizing photons contribute first to the, first to the galaxies, and then maybe to cosmic reionization as well. And we're going to also go through a little bit the stripped stars as gravitational wave sources. So let's start with what are these stripped stars. So just so that we are all 5 years ago. So what just happened here? We had the most massive star in the system that evolved faster than its companion because it is more massive. So it tried to swell up to become a red supergiant, but at some point the outer layers of the star felt a stronger gravitational pull towards the companion than to itself. And that starts the mass transfer, which causes the second star to both gain mass and spin up from that mass accretion. So in the end, most of that hydrogen-rich envelope is lost. And what you can see, what is left over is that hot and compact helium core. So that's why this star is labeled blue. And we can look at something maybe more serious diagram here. So for example, the Hertzsprung-Russell diagram with the stellar evolution track. This is models that I computed with the stellar evolution code MESA. You can see temperature going in the reverse direction on the x-axis. So this is the surface temperature, and the luminosity on the y-axis. Here is the evolutionary track of a 12 solar mass single star. It starts off relatively blue, and it evolves to redder and redder color, eventually exploding as a type 2 supernova, hydrogen-rich supernova. In the blue shading here, you can see the fraction of the emitted flux that is ionizing. So this 12 solar mass single star is relatively useless as a source of ionizing radiation. But the picture changes if the star is stripped. So here you can see the mass transfer phase. And as you start to see that hot and compact helium core, the track changes direction, moving to this really highly ionizing regime. Eventually, it then swells up during the helium shell burning and explodes as a 1b supernova in this case. So these kind of models, I wanted to highlight that they are not really new. These kind of simulations have been made for a long time, and there are some really nice photos actually from the 50s, 60s. So these photos are from 1957, when in Göttingen they were computing stellar evolution tracks using this computer here, and here reading out the output of the stellar evolution computation in this group. And it's the group of Kippenhagen. I think that this is Hofmeister. Yeah, and so this binary star was computed about 10 years later, and you can see that even though they couldn't resolve that Roslob overflow phase, the track still doesn't look that bad. So this has been going on for quite some time, but I still think that we have quite a lot of things to still learn about these stripped stars. And so let's go back to this diagram. So most of the time after mass transfer, the star spends as a stripped star over here during the central helium burning. So I was curious, how much ionizing emission does that star actually emit, right? So because the best you can do with the stellar evolution code is this. You can compute the Planck curve, a black body type spectrum. So here we have wavelength and flux. And this is not particularly accurate. We know that stars don't have black body type spectra. So to accurately estimate how much ionizing emission this really hot stripped star has, I used the surface properties computed from the stellar evolution model as input at the base of a wind in a radiative transfer code called CMFGen. And as output, we got something like this instead. So this may look significantly different, especially in this part of the spectrum, which is the helium-2 ionizing part of the spectrum. But in the rest of the spectrum, it actually follows quite closely the black body estimate. So it produces relatively well helium-1 and hydrogen ionizing flux. We can also talk about helium-2 ionizing flux. That's interesting, but I actually didn't put in some slides on that. So in this case, for this 4 solar mass stripped star that was created from that 12 solar mass donor, the ionizing flux, the fraction of the emitted ionizing flux is 83%. So it's really quite a lot. And it gives a little bit of perspective on that star. It must be really quite faint in the optical regime or so. So I made these as evolutionary models and spectral models for stripped stars for a range of mass, because mass transfer is not really a mass-dependent process, right? It can occur for any type of mass of star. And from that, we can summarize the properties that we expect for stripped stars. So first, they should be hot, between maybe 30 and 100,000 Kelvin, and really small, like less than a solar radius, maybe down to 0.1 solar radius or something like this. They cover a range of luminosities from maybe 10 to a million solar luminosities. And this has just to do with the mass of the star. So the more massive star, the more luminous it is. And the surface should be helium rich and hydrogen poor, simply because we don't have anymore that hydrogen rich envelope. So if I ask you, what kind of star is this? Some people may say, oh, I know, that's a Wolf-Rayet star, while others may say, no, that's a subdwarf. So neither of these answers are wrong. If we look at the mass range of helium stars, so here you can see the initial mass of a star, sort of corresponding to the mass of a strict star. Then at the low mass end, we have the subdwarfs, and at the high mass end, there are the Wolf-Rayet stars. Oh, oops. And we're going to look into this in-between regime a little bit later also, but for now, let's cover the entire mass range. So how does it look like in the spectral models that I made? These are the spectral models from the low mass end in purple through the intermediate mass end in blue to the high mass end in green. And it's increasing with mass like this. So you can see that most of them emit a large amount of their flux as ionizing photons. Here is the hydrogen ionization edge. And how do they then look in the optical? What kind of star is this? So let's look at the optical spectra. This is maybe not my best plot. I should definitely update this for the talks, but the main point is here, when we look at the optical spectrum, in the low mass end, we see absorption type spectrum, something that is characteristic to subdwarfs. And in the high mass end, we see emission line spectrum, which is something that's characteristic for Wolf-Rayet stars. So what's in between? I thought that initially that it would be a smooth transition where all the lines change subsequently from absorption to emission, but the lines change at different times, right? So here we have at some stages absorption lines and emission lines at the same time. So this is a signature of a weak stellar wind that then the spectrum should look something like this, so with both absorption and emission lines. And this has actually been found pretty recently, and I think it's a quite exciting discovery. So it was during a survey for Wolf-Rayet stars in the large and small Magellanic Clouds. So it was made by Phil Massey and collaborators, where they tie the large and small Magellanic Cloud using narrowband filters. So this feature here is a really characteristic feature of Wolf-Rayet stars, it's a helium-2 line. And so if you compare the narrowband WN filter here with a continuum filter in green, you should be able to pick up the stars that have this emission line. So what they found were stars that looked like this. So this is was called the WN303 star, named in this way because it has the emission features of a WN3 star, that's a type of Wolf-Rayet star, and the absorption features characteristic to an O3 star, so it's a really hot, a massive main sequence star. So an O3 star is much brighter than what these stars were. So that already discards the idea that it could be a binary composed of these two components. But it does show the indication of a really weak wind, which, at least in my mind, is interesting for the origin of these emission line and absorption line stars. Did they really have strong enough wind in order to create them, to blow up? Must they be the product of binary interaction? At the moment, I was curious if it matched the spectral models that I created. And this is just a simple overlay, but what you can see is that indeed the absorption features are at the right place, and there are matching emission features as well. So even though they don't match perfectly, it is an indication that what you are seeing here is the weak wind. So let's move on from what are the stripped stars to the ionizing photons and the implications of the ionizing photon emission from stripped stars. So first we're going to talk about the effect on the host galaxy, and second, the contribution to cosmic reionization. So where do ionizing radiation come from? What do we usually think about? Usually considered are these accreting supermassive black holes, AGNs, and stars. So let's focus on the stars because it can be quite it's possible to disentangle from galaxies which galaxies contain a supermassive black hole and why that's the reason for the ionizing radiation. So if we look at stars, usually massive stars are considered as the sources of ionizing emission, and of these we consider most of the time the most massive main sequence stars, OB-type main sequence stars, and Wolf-Rayet stars. So that's it. That's what produces the ionizing emission in traditional spectral synthesis codes, such as the Starvis 99 or Roussel and Charlot, FSPS, etc. Sometimes rotation and rotating stars are included, but there is actually much more ionizing photons emission. So we have X-ray binaries can produce some ionizing emission. The strip stars we've just been talking about, and they can also come from low mass stars. And the low mass stars, they can create as well post-AGB stars that can produce ionizing emission. And also accreting white dwarfs may be quite interesting as sources of ionizing radiation. So I'll be happy to talk about all of these objects, but today we're going to focus on the stripped stars and how they look like and what they can do to change the spectrum of a distant galaxy. So if we look at the emission rate of hydrogen ionizing photons, here shown in log scale, as function of time after a starburst for a stellar population of initially 1 million solar masses. This is the curve for when you include only single massive stars. So after about 3 million years, this curve drops. And since this is log scale, this is really quite a sharp drop because the most massive stars in the population start to die. When you include the stripped stars, they boost the ionizing emission, but at later times, because they are created from stars also at lower masses, they start to contribute maybe at 10 million years, boost the ionizing emission by a factor of 10, and after about 100 million years, their contribution, their boost is several orders of magnitude. So how does it look like? If we look at the spectrum, spectral energy distribution, this is for now a full population. So you have the wavelength on the x-axis and the luminosity on the y-axis. And this is after 20 million years after a starburst. So in green, that's the contribution from the massive stars. And in blue, that's the contribution from the stripped stars. So we can really see that apart from producing much more ionizing photons, these ionizing photons are also much harder. So they are much more energetic and can ionize, for example, even helium-2, as shown in this figure. So why is it, if there is such a dramatic contribution, that we haven't talked so much about these stripped stars, and how come we haven't seen them in distant stellar population, maybe younger and smaller stellar populations which are more bursty in terms of their star formation rate? So it has to do with their contribution to visible, detectable wavelength ranges. Over here we have the optical, and that's the ultraviolet. And these two are observable from ground and space. We have instruments, but at these wavelength ranges, the contribution from the stripped stars is less than 1% to the total flux. So it's really easy to outshine their contribution. Also, there is no strong stellar line that can pierce through this really bright continuum either. So it's really quite hard to see them directly. Over here in the ionizing regime, they really dominate, but the ionizing photons are easily absorbed by surrounding gas or actually neutral gas around the Earth. So this is not directly observable, which leads us to think that maybe we need to take a different approach in order to find whether these drift stars actually exist in these distant populations or not. So what can we do? If we look at this simple cartoon here, and we cannot expect then that the starlight reaches the telescope actually is going to be possible to use to detect these drift stars. We might be able to use surrounding gas emission lines. So when the stellar population shines on gas in its own galaxy, it ionizes and excites that gas and make the nebula, this gas, to shine differently compared to if there would not have been any strict stars. So what do I really mean with that? Let's look a little bit closer. This is again a spectral energy distribution, but now flipped. So we look at it as function of photon energy, and it's cut at the hydrogen ionization edge at 13.6 electron volts. So it increases the energy of the photons here. It's also normalized in the luminosity so that we can look at the hardness of the ionizing emission. And this in gray is the contribution from massive stars. When you also include the strict stars, you can see that the ionizing emission becomes much harder. It flattens out here. And even after 100 million years, it is harder than the hardest it is when there is only the massive stars. So how does that affect the surrounding nebula? We can look, for example, at the helium ionization edges. Here we have helium-1 to helium-2, which suggests that all these photons here can ionize neutral helium and create recombination lines in helium-1, for example. And this little chunk over here can ionize helium fully, providing helium-2 recombination lines. I think that that's quite interesting, but it is still quite uncertain how much of the photons are here and whether that's enough to produce a significant amount of helium-2 emission lines in distant galaxies. So this is something that has been observed in quite a few galaxies, actually, helium-2 emission lines, and I think it's still quite a mystery. So we're looking into whether it could be more than what this figure shows. Other ions, I mean, we can look at oxygen. So oxygen shines as collisional excitation. So what you would see here from from these photons of oxygen-1 to oxygen-2 ionized ionizing photons, is you can see then oxygen-2 lines in the nebula, and this is photons that can ionize oxygen-2 to oxygen-3 and therefore produce oxygen-3 lines in the nebula. So the O3 to O2 ratio should be larger for stellar population containing a lot of ionizing strict stars. I really like the carbon ionization edges because there is really quite a lot of carbon-3 to carbon-4 ionizing flux. And that is something that massive stars have a really hard time to produce. But it's at the same time something that has been started to be detected in nearby galaxies and its nebulars. This is from a work of Danielle Berg in 2019, where she detected these carbon-4 features, nebular carbon-4 features in a nearby galaxy, I think it is in this case. So these extra ionizing photons, how do they contribute at high redshift? At high redshift, the galaxies they were really quite small, right? So then sometimes they went through a burst, and then there was no star formation going on for a while, and then another burst. So this allows for the domination of strict stars. So if we look at this diagram, if there is 10 million years or so, then for sure the strict stars are going to dominate the ionization. And this is something that, together with the students Amy Secunda and Elizabeth Berthin, we were looking into by assigning or using this ionizing emission rate for stellar populations in a cosmological simulation that contains different sized halos. So this diagram is maybe a little bit complicated, but what we have on the x-axis is the mass of the halo, and I took the liberty to convert it to the stellar mass of the stellar population in a very, very rough way on the top. And the emission of ionizing photons is seen on the y-axis. So for the most massive systems, there is very little difference between these curves. So the purple is when you only include the single stars, and the green is when you also include the strip stars. But for the lower mass systems, which are the most common at this time in the universe evolution, the strip star really boosted the ionizing emission by a factor of 100 or so. So it's really quite a big difference in how these galaxies looked like at that time in terms of the ionizing flux. So just because they are fainter than the massive systems, they may not have completely super much boosted the ionizing emission, but these galaxies should really have looked quite different. And we were curious whether it's something that could be detectable, for example, with JWST. And so Elizabeth made this estimate where you can see the brightness of these galaxies as and in a histogram here, and the ones over here are the ones that would be detectable with JWST. So it's a really, really small fraction, but this is for a cosmological simulation at redshift 7. And I think it's quite interesting to think about how would this look like at redshift 5, for example, when the galaxies are still relatively small. Maybe then a much larger fraction can be detectable with JWST. So this is something that we still need to look closer into. So how much photons did they actually contribute during these early times, during the cosmic reionization epoch? If you just sum up the production of ionizing photons from a stellar population, massive stars contribute maybe 95% and strip stars just 5%. So it's really not so encouraging. But given that they are created with a delay compared to the massive stars, many of the massive stars will already have exploded, creating large holes in the surrounding gas. So that allows the ionizing photons from strip stars to reach the intergalactic medium much easier than most of the ionizing photons produced by massive stars. That those tend to be blocked out by that surrounding nebula. And if you account for that in a really simple way, accounting for the clouds, maybe the strip stars could have contributed tens of percent or something like that at these early times. So let's look at how it can have looked like. Here I convolve the emission rate of ionizing photons with the cosmic star formation rate. And you can see that this is a function of redshift, and this is basically just the emission rate of ionizing photons that reach the intergalactic medium. So at high redshifts, the strip stars were not as important as the massive star, but with the decreasing redshift, their importance increases. And in fact, they I think it is at a redshift 7 or so, they have about a quarter. So how does that affect the cosmic reionization? Here is a simple model where you balance the flux of ionizing photons into the intergalactic medium with the density of the intergalactic medium, and the neutrality, how neutral the intergalactic medium is. So it shows the fraction of hydrogen in the intergalactic medium that is ionized. So here is 0 is ionized, and that's fully ionized as function of redshift. So with only massive stars, you can see it starts early on here, but it doesn't become completely ionized until redshift 5.8, I think. When you include the strip stars, the reionization is complete about 100 billion years earlier. So we can look here with only single stars at redshift 5.8, and including the strip stars at redshift 6.5. And this corresponds to about 100 million years, which is really quite a lot of time actually at these early ages. As you can see, the age of the universe at that time was only like 700 million years, 1 giga-year or something like that. So this is, and I should say this is a rough model, and just basically to prove the point that they could have been important, but there is still much room for improvement in, for example, including them in a real cosmological simulation, and also better understand whether there is some way that we can infer whether these trip stars actually existed at that time. So took the liberty to took the liberty to elaborate a little bit on how they could be detectable. So this is now the emerging luminosity, so to say, of these ionizing photons. And this is when you only include the massive stars. When you include the stripped stars, this hardens actually quite a bit, especially in the helium-1 ionizing emission. So how can that affect the intergalactic medium in an observable way? First, for example, it can produce ionization of circumgalactic medium so that the circumgalactic medium reaches high ionization states. And this can be detectable by looking at distant quasars. So for example, carbon-4 absorption has been found in this way. Also, it could lead to heating of the intergalactic medium, but this is still something that is much under research, I think, to better understand the temperature of the intergalactic medium at early times. So there is quite some exciting predictions, but still relatively uncertain. So with that, let's move away from the ionizing photons and go to the gravitational wave sources. So I'm sure you're quite familiar with the diagram I'm about to show you, but I want to highlight a specific part in this diagram that I think has not caught that much attention. So it starts off with two stars in a binary. The most massive star in the system evolves first, transfers its material, its envelope, to the companion star and becomes a stripped star. This stripped star eventually evolves into a compact object, and if the system is still bound, it likely has a large mass ratio, which gives rise to, next time interaction occurs, it's probably going to be unstable, initiating a common envelope phase. And if this doesn't lead to a merger, what you're left with is a really tight system composed of a compact object and a stripped star. It may or may not interact again, but eventually that stripped star is going to create another compact object. And if that system remains bound, and it's tight enough, it may merge in, for example, a binary neutron star merger event, a kilonova, etc., creating something visible that we've been detecting with LIGO and Virgo. So just looking at the gravitational wave frequency of binaries here, it's really quite a simple formula. 2 over the orbital period. So down here, the period is of order seconds, which means that the gravitational wave frequency should be less than kilohertz. That's the LIGO regime. But actually, over here, the orbital period should be of order hours, which can possibly be detectable with this proposed mission, the space mission LISA, that is going to fly in about 15 years or so. So here's an artist's impression where there is this huge 5 million kilometer arms in this observatory that's supposed to trail the orbit of the Earth. So I got really curious about this, whether these...
Sorry,
yes.
I didn't quite follow in like stage 10. What masses do the final compact objects have?
Yes, we haven't really reached there yet, but these would be, for example, white dwarfs, neutron stars, and potentially even black holes. In the population I'm about to describe, I did not include the black holes yet, but they definitely can also be a part of this story. Curious about these living sources of gravitational waves, because you know the stripped star is still undergoing nuclear fusion in the center, so it still shines. It's very different compared to what we usually consider a gravitational wave source. right? So I wanted to make an estimate for how large is this population, how many of these stars may we be able to detect with LISA. And so to do that, I started with the population model that I described during the ionizing part of this talk. So it's just considering the first 3 stages here. The next stages are really quite complicated because you need to go through a supernova explosion, and we don't really know what is the kick of the compact object after a supernova explosion in the case of neutron stars, or even like the creation of a white dwarf. How does it work? And then we have a common envelope stage, and the common envelope stage is really not very well understood. We don't know what is the orbital period after a common envelope ejection and how easily a common envelope is ejected. So I took a shortcut here and said, okay, let's consider that about 10% of these systems are going to survive to this stage, and that they will have short orbital periods of the minimum possible orbital period up to 3 times the minimum possible orbital period. That corresponds to periods of up to 10 hours or something like this. And then I just distributed these systems. It's a Monte Carlo code, distributed them in the Milky Way following the star formation. Since these are still relatively young objects, they should not be in the halo. And as a result, let's look at this gravitational wave strain diagram. So we have gravitational wave frequency on the x-axis and the strength of the gravitational waves on the y-axis. And this is the sensitivity curve of LISA. So in the white area, that's a detectable region, and in gray, it's not detectable. So the population I made, it ended up here in the low frequency regime of the LISA detectable range. And in dark blue, that's strip stars orbiting neutron stars, and in the lighter blue, that's strip stars orbiting white dwarfs. They are limited by the radius of the star in this case, simply because I did not make careful models for what happens when you start a second mass transfer phase. So all of these are actually undergoing mass transfer and can be much tighter objects, CVs, for example, or X-ray binaries, ultraluminous X-ray sources, etc. In this particular run, there was about there was actually exactly 5 systems that were found to have signal to noise ratio above 5. And of these, there are 4 strip stars orbiting white dwarf and 1 orbiting a neutron star. And there are actually already a few systems that are known. So these CD-30 and CTFJ2130 are white dwarfs orbiting subdwarfs, so low mass strip stars. So it cannot be too off, this estimate, but you can see that CTFJ2130 has a higher frequency, and this is simply because this is actually interacting. So there could be a larger population over here. Depending on how you assume the period distribution for this population after the common envelope, you can really change what is the number of detectable systems. So it's between maybe 0 and 100, but we know that it's not 0. There should be at least 2. And so this is the number of detectable stars are actually quite sensitive to these uncertain physical properties in binary evolution. So, oh yeah, that's the double white dwarfs. Maybe interested to see where the double white dwarfs are. They reach higher frequencies. So actually, from these systems, we may be able to better understand what is the orbital periods after common envelope phase, and how small can actually strip stars become. These are 2 things that are remain quite uncertain when it comes to strip stars and binary interaction. So how can we find these? I got a little bit impatient. I mean, LISA is launching in 15 years or so, so it's actually quite some time. In terms of brightness, these are much brighter than, for example, the typical LISA sources, the double white dwarfs, because the strip star is still shining. So you may be able to detect them just from the brightness, but the brightness variability is something that has been used to find, for example, that interacting source. And that comes from the fact that the star is so tight. So the stripped star becomes deformed, and as you see it orbit in the motion in the orbit as it moves, you see more or less of the surface, and therefore it changes in variability. So this has been used using the CDF. Also, the orbital motion is really fast. So many of these should have really high radial velocity shifts of over 250 kilometers per second. I hope maybe SDSS5 can help with this, or Foremost, etc. But maybe the most exciting part is that when you have a compact object moving so close to a star, a stripped star, it is actually moving through the stellar wind of that star, and it can that way create a little accretion that may shine in X-rays. So I was curious how much X-ray emission we expect these systems to have, and so I followed the Bondi-Hoyle accretion of the compact objects and estimated the X-ray luminosity with this simple formula. So here we have the X-ray luminosity on the y-axis, and the x-axis is the mass of the stripped star, but it's basically a proxy of the wind mass loss. These are orbiting neutron stars. Each of them is actually a y-axis. You can see that they should have X-ray luminosities between 10 to 33 to 10 to 36 ergs per second. So this is quite faint for X-ray binaries. So, and given that these are actually about 5,000 systems in the galaxy, is the estimate. This is predicting that there should be this faint X-ray faint type of X-ray binaries that are yet to be discovered, and yeah, that's quite fun. In the lower mass regime, so this is stripped stars orbiting white dwarfs, their X-ray luminosity is much less. But if the system is close enough, you might be able to anyway detect that. So with that, let's summarize this part, and I will go into the last part of the seminar. So we talk about what are stripped stars, the ionizing photons, and stripped stars as gravitational wave sources. And to remember from this, the stripped stars are hot and small, helium-rich, and they produce a lot of ionizing radiation. The stripped stars, they have so much ionizing radiation that they can boost the emission from stellar populations by some orders of magnitude. And it's possible, but that because they provide so much hard ionizing radiation, that they can leave observable traces in bursty star-forming galaxies. And it's also possible that stripped stars, when they orbit a compact object really tight, they may be detectable by LISA, and can also constitute this X-ray faint type of X-ray binaries. But now let's go into something I think we can call a paradox. So theory predicts that about a third of all massive stars should become stripped. But do you know of any stripped stars? There are about a dozen or so, I would say, are confirmed. And here we have a list. This is maybe a little bit outdated, because these ones here, I think we have also confirmed that they are B stars orbiting low mass substars. So there's only one actually, which is the star here, HD 45166, that has a mass that is in the intermediate mass regime. And this, even though we have 15 systems here, I mean, that doesn't really correspond to that third of all massive stars. So where are all the stripped stars? Are they missing? Are we doing something wrong in theory? Is that would really affect, the creation of merging binary neutron stars, or yeah, for example, that, or the supernova origin of the hydrogen poor supernovae? Or did we just not find them yet? And how is that possible if there should be a few observed systems? and highlight a bit of work about these lower mass systems that I think that was done really well. This is done by Luchan Wang. And Luchan, how she did this, she was looking for rapidly spinning BE stars and using a cross correlation of spectra in the ultraviolet to infer the presence of a stripped companion. So we expect that the companion of a stripped star should be rapidly spinning from the mass transfer, but it can be hard to see simply because it's faint in the optical. So she could find, here is an example of like the blackest observed curve, and she could find using this template for a hot star, the presence of a faint hot companion using cross correlation. Here you can see 3 different epochs of her HST data, this system. So she did this for about for 10 systems she could find, and this is a Hertz progressive diagram showing you actually my evolutionary tracks here for low mass systems, subdwarf of 0.6 to 0.9-ish solar masses. For these color dots are the new ones down here. So this is the way she could find low mass companions to these BE stars. These BE stars are of early type. So, and also from the flux ratios that she could infer, it was really clear that the BE stars are much more massive than these subdwarf companions. And I think that this is one of the best evidences we have that this previous mass transfer in these cases must have been quite conservative. And that is something that we are still struggling with understanding, how conservative is mass transfer. So we're starting, I think, here, but there is still a lot of work to do, given that this is still in the very low mass regime. So if we look at a diagram like this of the mass of the stripped star, the mass of the companion, we can place different stars inside of this diagram of the known systems. So here are some that, slide I just skipped actually. So inflated systems, very, very low mass stars. Over here are those WN303 stars I was talking about earlier. And there are the stars from Luchan Wang. And then there are quite a few subdwarfs at the low mass end, maybe orbiting white dwarfs or so. Beta Lyra, you remember from the beginning, the mass transferring system from the Chara array. And there's a helium giant called Upsilon Sagittarius, maybe has 2 solar masses or so. There is that only intermediate mass system, HD 45166. But basically, I mean, this is largely empty, this part of the parameter space. And this is where we expect that the progenitors of 2b, 1bc supernovae, binary neutron star mergers, and neutron star binary black hole mergers should reside. So really, if we don't find this, there is a problem with the theory. So together with my collaborators, Maria Drought and Bethany Ludwig, we started a search for these stripped stars. And you can see we used this image. This is an ultraviolet image from the Swift satellite. So I will go a little bit to show you what we used it for. So how do you identify these intermediate mass stripped stars? If we look at, this is theoretical models of color magnitude diagram. So the B minus V optical colors, V of a stellar population, and in black that's regular evolving stars, and then we have in blue binaries that contain a stripped companion. And they really sort of overlap. It's really hard to identify them using just this. But if you use that as a UV, you get a small part of the population. This is about 20% that separate out as UV bright sources in this UV color magnitude diagram. So why is that? Why is it working? Here is spectral energy distributions of 3 different stripped stars, so dark blue, medium blue, and light blue, and a B-type main sequence star. And if we imagine that this B-type main sequence star is a companion for each of these stripped stars, we can estimate how much flux it should contribute in different wavelength ranges. So in the visible for both of the lower mass systems, the B star is actually quite bright. But for all stars, in the ultraviolet, the strip star is dominating. So this way, you can produce UV bright sources, even though in the B and V band, you didn't see any indication of a hot component. So we use this using the regular V band. I think it's data from the SWAP telescope as Las Campanas, and the UV filter from Swift archival data. And so this is a more realistic population prediction for the LMC, and this is how it looks like in reality in the LMC and in the SNC. And the purple dots here are models for stripped stars and isolated stripped stars that I created. In the dark diamonds, these are Wolf-Rayet stars in the LMC and SMC, and the medium blue diamonds are those WN303 stars that happen to be in the tiles of the Swift data. And so I think it looks really nice because there is a large number of candidates in both of the clouds. So this is several dates. And we wanted to confirm the stars. We did that by observing their optical spectrum, trying to find the signature of a hot component. So I will show you, we found that there was 3 main spectral types, so to say, for these UV bright stars. And so here is how they look like in the optical. So we have helium-2 lines in the 2 top ones, which is really quite a good signature of high effective temperature. And in some of the cases, we have also signs of Balmer lines, which is really quite a good signature of a B star. So they are sort of contradicting, but given that these most likely are binaries, right, you should be able to see in some cases the contribution from both stars. So the helium-2 lines in combination with some Balmer lines. And if the companion is a really low mass or a compact object, you may only see the strip star.
Excuse me, Ylva.
So yes.
Sorry to interrupt you, but
sure.
I'm a little confused here. You have a series of stars that seem to be showing, well, that show helium-2 lines in absorption, and the Balmer series in absorption. And I don't understand what is peculiar about them. I mean, Nolan Walborn has and many other people have their spectral classification schemes, and there's a quantitative method of determining temperatures and gravities and whatever. So I don't understand what makes these stars in particular unusual, that you could classify them as a binary and a stripped binary at that.
That's very good that you highlight this. So let me show you one part. O stars are stars that tend to have helium-2 lines. B stars are not expected to have helium-2 lines. O stars are located over here, right? So they have the right temperature, but these objects are much fainter. So maybe you think, what if extinction did this, right? But reddening extinction vector is going in this direction. So it cannot really be any O stars.
But fainter does not mean colder. No, you have nuclei of planetary nebula that are at 100,000 degrees, and they are very faint, and they still have, they have high ionization lines. So well, I guess, well, we can keep this for the end of the talk.
That is true. Let me mention the central stars of planetary nebulae, though. They are clearly the central stars of planetary nebulae, whilst these stars are not central stars of planetary nebulae. There is no nebula, a planetary nebula surrounding these objects. And they also show helium enrichment and not the signatures of becoming a carbon-oxygen white dwarf, for example, or anything like this. There is very little signature that these have. less stellar winds. So some of them even show contradicting temperature measurements, like this one in the middle, for example. For a star with helium-2 lines, you should not be able to have these strong short wavelength Balmer lines. It does not work. This is very hard to fit a spectrum to this star, assuming it is a single star. So, but hopefully this is something I can show better in the paper. We used spectral fitting to get stellar properties for these systems, and we could place them then in the Hertzsprung-Russell diagram. Maybe this is more convincing, Gloria. So this is Hertzsprung-Russell diagrams with the stellar evolution tracks of envelope stripped stars using mass transfer in the LMC and SMC, and you can see the helium core burning phase is here, 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 and here. And they are labeled with the mass of the star. And we can see that these systems, these 10 stars, they overlap with the predictions for 2 to 8 solar mass stripped stars, mostly. There is one that is a little bit lower mass, maybe a little bit inflated as well. But to me, I should say maybe the spectral fitting grid that we used, it is covering a large range of temperatures, a large range of surface hydrogen mass fraction, and surface gravity. And all of this implies that these stars have high surface gravity and should be located here. Then whether they are anything else, this is something that me and Maria are working much on to disprove. And concerning also the post-AGB stars, low mass stars, that phase is very, very short lasting. So we estimate that there should only be about 1 or so in the Magellanic Clouds each. But that's something that we are going to quantify better. Anyway, so to sum it up, where does it end up? I think that our new survey is sensitive to this part of the parameter space, and we're starting to fill in objects in here. We're currently doing radial velocity monitoring of the systems, and so far, all the ones that we have more than, I think, 3 spectra for have shown significant shifts in radial velocity. So to finish up, then let's complement this slide with that we think that we have discovered a first sample of these intermediate mass stars that are stripped in binaries. And with that, yeah, I would be happy to open a discussion, and if you have any questions, I'd be happy to answer as well. So thank you so much for your attention, and hope you could find some of it interesting.
So thank you very much, Ylva.